Okay, so let's go. First, I will write a bit about philosophy. So there is a bit of difference between mathematics is kind of unique area where some philosophical issues are very different. Then I will quickly describe the structure of a mathematical research paper. Then I will speak about direct language. So the idea, the intended idea is, what if you come from another area and you want to publish a paper in mathematics, or you have a mathematical result and you want to publish it. So I want to prepare you for this. So when you come from the wrong background, how can you still write something? Okay, after I say something about the structure of research paper, I will speak a bit about English. What English, so tips on using English with many examples from mathematics. Then I will explain how to avoid formulas. Then I will say something about how to structure your proof better. And I will give you some useful tools. I think for some of you, this will be the most important part of the talk. And in the end, I will, there is some task where you can rewrite something better. So we will discuss how to formulate things. Okay, so let's start with the philosophical part. And before I start with the talk, let me say this, that if there are people in pure mathematics, at this level, maybe I'm not a good writer. There are people who write books very fast. I'm a slow writer. But at least I've published many papers that got accepted, and even some compliments on my writing. I will tell you a lot of rules. All these rules have counterexamples. So there are things that are important. And when you have an actual problem, you want to say something, and you go over all possible options to say it, then you can see that each option violates some rule. And then you need to think which rule I'm going to violate. So the plan is to tell the rules so that you can then violate them, but from an informed perspective. And then you cannot learn how to write by listening to a talk. So you can only learn to write by actually writing. So it would be good to listen to this talk again after you have more experience. Okay, so let's go with the philosophy. So people want, so I expected that you were PhD students and you want to have academic career. And people think I need to be able to write well in order to be able to publish my papers. But actually the reason is much more important. So when you write mathematical arguments, what you're training is, you train how to make very convincing arguments. So in math, something is considered true if it's very convincing. And so writing proofs is closely related to teaching, which is also a very important aspect of an academic career. So if a person who can write well can also teach well, and people who teach well usually write well. No perfect correlation. But it even goes deeper. If you want to prove a theorem yourself, if you want to find proofs, it's again the same skill as writing proofs. And so what are these skills? So first is the dangerous word obvious in mathematics. So whenever you want to write obvious, you need to be extremely careful, because you want to write obvious when you are not conscious about the reason why some reasoning step is true. It means information is hidden in your brain. You're not aware of something. So it might be that the thing is hidden is indeed something trivial, but very often it's some reasoning step that's wrong, or a reasoning step that's the key to a very genius idea. So writing forces you to reveal all little steps. And that's why during writing, people get amazing ideas to make progress in their first step. Also, the better you write. Writing well means suppressing all irrelevant details. But if you can suppress irrelevant details, you can also think better. You can also figure out what are the right definitions. So writing well means creating a language, and thinking goes by language. So it's just, why do you need to write well? It's just everything what you ever will do in a career is connected to the skills, to the skill. Okay. So then writing mathematics, the focus should be on writing things beautifully. So if you invent something in math, then the end product is measured by its beauty by other professional mathematicians. So mathematicians, they like to say that their work is kind of art. And so here, Hardy is one of the best mathematicians that has ever lived, and he has written memoirs before he died, which are very famous. And here is a quote for it. So the full quote is usually abbreviated by, "There is no permanent place for ugly mathematics." So whatever you produce in math needs to be formulated, and it is like as important, like you can be a painter, have an idea of a painting, but then the way you actually paint it is as important as your idea. And so that's, if you write a paper, the writing itself is as important as the content. And so here is an experience that I think I invent something, and because I'm naive, I think I've had something great, and then I write it. But by keeping to polish in many iterations, it has happened that some poor paper actually becomes very good compared to my level of my other papers. Okay, and so in other areas of science, so in mathematics, things are quite clean in the sense that people are very focused on research, and they want to increase their level further and further. But I also work in computer science. I'm in the computer science department, and HSE has excellent department, but like in the rest of the world, there is a rotten situation. So where there are people, so evaluations happens like based on quantitative measures. How many papers do you publish? How long is your CV? How many courses do you teach? And the hiring committees do not actually read the papers. And so what people do is that they create a lot of articles that get accepted by careless reviewers. And there, the idea is not to write things beautifully, but like to conceal that there is no content. So to hide that there is no content, and people do it behind complicated formulations. And so advice in this talk can be used in both directions. So if you have nice content and want to be understood, then use the direction I tell you. But you can go in the other direction. If you have nothing to say, then you can go in the other direction. For a nice example is nominalizations. So where you transform a verb to a noun. For example, the purpose of the operation is the denazification of blah, blah, blah. So then there is a specific activity, but this activity is kind of covered in abstract words, and people do not think about this activity. Okay, yes, yeah, so politicians all the time do it in the other direction. I mean, not only in Russia, in Belgium, perhaps even more than in Russia. Okay, and this is kind of old problem in science. It started in more than 300 years ago. There were maybe not so many universities, but there was like Royal Society of London for Improvement of Natural Knowledge. And so there was a guy who was sick of all this verbose prosa, and he wrote a call to stop with this. And funny enough, the way how he asks to be short and clear is terribly involved and terribly complicated and completely unreadable. Okay, but this is kind of introductory observations. Okay. So let's go to the right mindset. And so a bad writer is a person who wants to prove something about himself. For example, he's clever, a hero, a victim, whatever. And also he is lazy, so he wants to write little, and then the reader has to figure out all the details. So a good writer is the opposite. So he wants to help the audience. He loves his readers. Even if there is only one reader or even no readers of his paper, he still loves them a lot. Then he wants to make reading as smooth as possible. So he does not want to think the reader to be about the language. So he does not want that the reader thinks about the language, only about the mathematical steps. So he is in some sense invisible, completely neutral. Okay, then if you start a career in math, you will get a lot of advice, especially from your advisor. But here you should know that successful advisors are not necessarily successful researchers. So my opinion is that sometimes there is negative correlation. So bad researchers have many PhD students. So actually they prefer managing PhD students over research. The key in being a good supervisor is actually give your student self-confidence that if he works, he will be rewarded. And by being stupid, an advisor spreads a lot of self-confidence because the students quickly realize they are more clever than him. And so they feel confident and they finish their PhD. And also the bad researcher teaches bad practices. Okay, so let us, okay, so why should you write well? So how can you like push yourself to write well? Just think that you write a paper and 10,000 people will read it. Now, your first paper, nobody will read it. But if you keep thinking that your paper is read by 10,000 people, eventually it will become true. So I was kind of shocked. I have lecture notes and already 100 people read it. And each time my course is bigger and bigger. And so maybe in some years, indeed, that will be the amount of people that have read the lecture notes of a certain course. Okay. So in all books about writing, they say that you should know your audience. And you should take a specific person in mind when you write. And I think it's true when you write a first draft, but personally, each time I revise it, I reformulate so that more and more people can understand things. Okay, so here is more philosophy. So the most important thing on this slide is linear smooth reading. So the paper will be read from the beginning till the end, and to understand the words, all previous words should be enough. So that's linear reading. Okay, but this is more than enough of philosophy. So let us speak a bit about what is a research paper. So in math, the point of a research paper is to tell proofs to other people of theorems that they cannot prove. So there are open questions. And if you can solve one of them, or your supervisor tells you an open question, you can solve it. Then you write down the proof, and then other people can use your theorem to build more complex theorems. And so important in the paper is that there are not too many results where you're most proud of. So you have a bunch of discoveries, then you call them and so you pick 1 to 3 of the most important results, you call them theorem. And that's the reviewer will look at these results to judge you. Then you can have more discoveries, but they're like minor discoveries. You should call them lemma or proposition. A lemma is something, a lemma is a result that is used inside a bigger proof. So it is some technical result that is used in the specific context of a more complex result. It's also used to denote a result with an easy proof. So it has two meanings. Proposition is the same as theorem, but the difference is that proposition is a theorem that's less important. Okay, and research papers, they have short introduction. So this lecture is mostly about research papers. Okay, there also exist overview papers. So in the research paper, there is an open question and people agree that it's an important open question. Then the question, so you might ask, where do the open questions come from? They come from overview papers. So people propose new lines of research. They explain why a certain problem is important. Usually old people write such papers. So they explain why it's important. Also like interdisciplinary research, interdisciplinary researchers. So if you come from economy and you discover that there is like a game theory or something, you discover that there is an important question, mathematical question that's relevant for the field, then you can write such an overview paper where you introduce a new program and ask the mathematicians to answer these mathematical questions. And so you can put there some hard proof, like a famous example is a paper of Nash in game theory, where he both introduced game theory to the mathematical community and proved a very important theorem. So the existing of Nash equilibriums. And he got the Nobel Prize for it. And then there is a second type of overview paper that are devoted to to systematically discuss all attempts to study an existing established open question. And such papers, they can contain minor new results. And I must say that in reviewing, I'm frustrated if a paper does not belong to a clear category, especially papers that are half systematical overview and half trying to solve an important problem. Because then everything is not optimized for either goal, and usually the author doesn't realize anything in either goal. So he's just thinking like, okay, my results are not good enough to publish. I will put some blah blah around quickly, and then one ends up with an annoying paper. And for a reviewer, it's always harder to reject a paper because that needs to be carefully motivated. Okay, so now let's go back to research papers, papers that solve open problems. Such papers can be very short. And here you see a paper, it contains a title and 2 sentences. And so there is an important question. So it's connected to Fermat's last question. And so is it possible that x to the power n plus y to the power n equals z to the power n for integers x, y, z? And so Euler's conjecture is a stronger version of this. And he says, can you have, is it possible that the sum of n powers of n nth powers equals another nth power? And then somebody found a counterexample. So very short paper. And in the Bulletin of American Mathematical Society, it's not top journal. It's not Journal of American Mathematical Society. That's probably the best one. But the Bulletin is also a pretty good journal. So it's in the, I think if you publish one, it's considered by HSC the highest level. I'm not sure, I didn't check it, but I assume it is like this. Okay, and here you see the one-page paper of John Nash that's worth Nobel Prize in Economy. So it starts in the left bottom, it ends in the right. So if you have content, then you want to convince it in a very concise, direct, and short way. clear, concise, direct, and short. So important results often are, important proofs are often of this type. So it's not true that the longer is your proof, the better is your paper. So experienced reviewer will see that you do not write optimally. Bad reviewers will not see it. And so this technique, yeah, so you can, sometimes these nasty games are played, but don't focus on this, focus on writing well. Okay, so abstracts are very easy to write in mathematics. You just tell, we show that, and then you prove, put your main result there. Sometimes you need a definition, and sometimes you need extra explanations why this result is interesting. For example, it implies some other result. Like Goldbach's conjecture is probably the most famous open problem. So imagine you prove some generalization of it, then you can say blah, blah, and blah, 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 define this question on this special structure, and we show that there exists such object with this property, and it's very important because it implies this Goldbach conjecture. And so that's short abstract, very easy to write, provided you have an interesting, proven something interesting. Then this is some general advice on that holds for all papers. You should have interesting opening sentence. It's like general advice. Okay, yeah, so like first impression is important. And then it is bad if you start with a long sequence of technical definitions. Like in the bottom, there is, if your first sentence is like this, let f be blah function, g blah blah function, the reader becomes tired immediately. He wants to know what's the paper about. Okay. Then some people do the opposite. They just say addition is important in mathematics and in computing. And so that there are just empty sentences that also the reader falls asleep. So that's the opposite of being too technical. And what happens a lot with beginning writers is that they just repeat the abstract in the introduction or take sentences from the abstract. This is again boring for the reader because he just read the abstract. Okay, then there is some introduction. So after the opening sentence, you need to review what literature already exists. Then you need to say formally. So then if you have a long paper, it is a good idea. I mean, long paper, say more than 6 pages or something. Then it's a good idea to state your theorems. And you want to convince that your theorems is beautiful. That means that it has some, it discusses something fundamental. And usually something fundamental can be introduced with very few definitions, and the statement of the theorem is very short. So there you prove yourself, and what you should do is optimize your research towards obtaining a result about some elegant definitions. Okay, and then you can, like in a few sentences, say something about the proof techniques that you use. This is optional. Now, what bad writers do, they create, after their introduction, well, first thing is that a first bad thing is that before the statement of the results, there are definitions used that are only used inside the proof. And so they give you, so if you measure quality by amount of definitions of the main result, then you're harming yourself in this way. So the second bad thing that people do is, after they've stated the theorems in optimal form, in very nice, concise form, they create a section notation. And they introduce the notation for all of the paper. But this notation will only be used near, some of the notation might only be used near the end. And so it's very boring to read something that you will not need for several hours, maybe weeks or days, days or weeks. So if I need to review a paper and it has a section notation that's more than half a page, then I know I'm gonna have a very bad day. And similar things about preliminaries. So after you have the section notation, then people give a section preliminaries about all the other results they will use. But it's better to just discuss these results right before you use them. Otherwise, your memory is full. And so your supervisor, the bad supervisor, will say, no, the notation section is very handy because whenever you forget something, you can go to the same section and read it there. But the thing is that for this to work, the reader should arrive by on your notation section and not suicide or, okay, this is a strong word, but I mean, not get depressed or run away from your paper. Okay, and here is a even top worst advice, the most worst advice, a supervisor that says, make a notation section. And when you write 4 papers, just use 4 times the notations, the same notation section. That means that you tell 4 different things, but you don't optimize your notation for each purpose separately. Okay. So let us now discuss a bit. I said that the formulation of the theorem is very important because that's how your paper will be judged. And so how can you make a formulation of your theorem ugly? One way to do it is introduce symbols in your notation that you do not use. So introduce symbols that appear only once or twice. For example, everyone knows a differential function, f is continuous. But note that in the statement of the theorem, f is used only once. So you can just drop it and it becomes already more beautiful. A theorem should be one short sentence. Now, if you cannot create a one short sentence, then it means that probably if your theorem is interesting, it means that you should give some extra definitions first. So the definitions should contain the longer sentences. And before the definition, you should explain why your concept is important. So there is a bad example. Suppose that there exists a constant c, a convex function g, and f, and a simplex s with following 3 cumbersome properties. And then you prove that your algorithm works well under these conditions. But it works well to find only a limited set of optimal solutions. Then this theorem, a cumbersome theorem, needs to be motivated very well. And so it needs to be explained why these assumptions are natural, why they appear somehow in an application, or why they are somehow elegant or naturally come together or something. So in this case, you better say that something like a simplex S. The simplex S is said to be smooth if there exist convex functions f and g that satisfy blah, 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 blah. And then there is the question, why is this definition interesting? And then you can make a theorem. Given a smooth simplex S, the optimization algorithm will find all local maxima that are also whatever, and then a new definition. So then you transform this cumbersome theorem to one simple theorem. So that's the solution if you have a cumbersome statement. Another solution is just strengthen your result. Keep working on it. and improve your algorithm such that it find all local maxima, for example. Then you don't need the conditions. That's usually what I spend a lot of time doing. Or another result is weaken the theorems. So maybe there is a weak, so here you have again constant C, functions f and g, and simplex s. Maybe there is a bit weaker condition, but that's much easier to formulate. And then you can state your theorem. But afterwards, you can make a remark and say, look, actually, my proof works under, so weaker theorem means you have a stronger condition. So stronger theorem means you have a weaker condition. So after stating the theorem, you can say, oh, my proof also works with a weaker assumption. Okay, and then listed there. Okay, so now let us, there's a lot of philosophy. Let us do a bit of very specific advice with some exercises. So after you've written your first draft, you can think about what the advices I'm gonna tell now. So your first draft will contain many complex words, long sentences, and you need to simplify the language. So that's what this section about. And so again, you want to let the reader focus on math. And so the brain should not be thinking about deconstructing grammar, deciphering grammar, unfolding unnecessary definitions, and so on. And so you should think that you can speak as well as a 5-year-old with simple words. The house is big. I eat apples. So you have to speak. You have to write like Donald Trump speaks. So just in strong form, be Donald Trump. Okay. So and in other sciences, there were also people who noticed this, and as usual, they call everyone to speak with the fewest words in clearest possible form. And so here it is editor of important journal on veterinary sciences. He calls his readers and his authors to write with the fewest possible words. And so rule 1 is drop unnecessary words. And so maybe you can tell me, so what means an unnecessary word? If you drop the word, the meaning doesn't change of your statement. So now is the question, can you find words in these sentences that can be safely dropped? So the main purpose of any scientific article is to convey in the fewest number of words. So is there something in the fewest number of words? What can be dropped there?
Main can be dropped, like
yeah, exactly.
enough.
Yeah, indeed. Yeah.
In the fewest number of words, just briefly.
Yeah, or just say in the fewest words. Idea, procedure, and conclusions of an investigator to the scientific community. Okay, that's right. Whether or not, okay, whether or not this blah, 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 blah. So whether or not, this or not has no function. Whether this admirable aim is accomplished works easily well. Depends to a large extent on how skillful the author is in assembling the words of the English language. So,
a large extent?
Yes, that can be dropped. And I would also drop, okay. I would just say how skillful the author is in the English language.
Or just in English?
Yeah, in English, even better. So just like a lot of words can just be dropped. So here is a proposal. The purpose of a scientific article is to convey in the fewest words ideas, procedures, and conclusions of an investigator. Whether this admirable aim, I would also drop, whether this aim is accomplished depends on how skillful the author is in the English. And it can even indeed be much shorter. A bad writer wants to convey that he is a smart person by using smart language. The other way is, if you have content, you can convey you're a smart person by saying some clever content. And then the difficult words, to large extent, they are harming you because they block the content. So again, be Donald Trump. So his words sound very silly. And then intellectuals sometimes do not understand that from time to time he says something clever. So when he is attacked, people, okay, that's a political opinion. First of all, I would never in my life vote for him, but but there is a reason why he can do successful things, and I believe this is true. And such people are dangerous.
Can I butt in just for a second?
Yeah.
When we want to beautify the language, it's about literature, I guess, because this is the function of literature. But when we write a research article, the most important thing is clarity. And the fewer words we use, the clearer the article will be. That's probably a better analogy or better comparison with literature.
Yeah. So, but you
Not
are
to
right.
mention politics, I mean.
Yeah. All advice can be used in two directions. If you have no content, then write to a large extent to make it sound better. So yeah, so my task is to sit in PhD seminar, and it's used for administration. They want to know whether student is actually doing research, and you can hear it after 4 sentences. What is the person trying to do? Sound clever or tell what he has discovered? Okay, but that's not for mathematics. So here are more exercises. So there is a sentence, remove all unnecessary words. There we can drop the word all. Okay, now real mathematics. For any given P, so which word can be dropped? For any P. For all sufficiently large C, all, can even more words be dropped?
Sufficiently?
Yeah, so you can just say for large C. And so you can say for large C, the limit of f of C is, for large C, f of C is smaller than 0.5. But the sentence for all sufficiently large C also does not say how large it should be. I must say that this is dangerous if you have two variables that need to be large. Then you cannot do it. So if you have both C and D have to be large, then the question is, how does the lower bound depend on C and D? And so I have cases where the reviewer complained about this because I applied it in this case with two variables. And I was unhappy because the trade-off was very difficult, but for all applications, it didn't matter. But I, of course, should have said, if the, okay, so then it's a slippery terrain. And so one reviewer complained, and I have no choice to in the revision to deal with it. Okay, which of the methods is better? So how can you shorten it? Okay, you need to modify one letter. So it's not just dropping. So how can you say it with less words? By essentially dropping words. Yeah, which method is better indeed, but singular. So you need to drop some words and the S from methods. We need X to be sufficiently small. How can you say it short? we need small x. Okay, that's not dropping, and moving x in the back is almost dropping. The proof is very hard. Just drop very. And on, okay, it's kind of warning to the reader. By the way, you can almost always drop very. So there is a work of Donald Knuth. Many people use it to improve their mathematical writing. And he said that you can only use very if you can replace it by damned. So the proof is damned hard. And then if this works, you're allowed to say very. But I never, almost never, I cannot remember I've ever used it. Okay, so here are the solutions. Okay, so now you can also drop too many words. So when you use if x then y, so people say, okay, why not say if x, y? Linguistically, it's okay. Mathematically, it's confusing, especially in the first example. If A equals B, C equals D, E equals F. So you should put then and also the end. You should so assume A as a group is linguistically correct, but it's smoother reading if you add this that. In more complex sentence, it will help. Also, you can say, if 2 pages ago you said that P is a natural number, then you can help to remind the reader. So not say that P belongs to S, just say the natural number P belongs to S. So they're so these words, strictly spoken, they're unnecessary, but it helps the reader to read it smooth without much thinking. Or if P represents the number of operators and the reader might have forgotten it, you can do the second example. Okay. So here are more exercises for unnecessary words. Section 4 is devoted to the study of blah, 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 blah. It's too easy question, I guess. So you can just drop the study. Let us denote by Z. For simplicity of notation, we drop subscripts. For simplicity of notations, but just we drop subscripts because of the fact that it's just first compute. Okay, sorry, this is a bad example. One can discuss, but usually you can drop first as well, or we now compute, and this now, there are often too many nows in the paper. Hence, we have x equals 1. How can you say it shorter? Equals 1, yeah, or hence it follows that x equals 1. By applying lemma 1, we conclude that that's just by lemma 1. So here are this, oops, my pointer, yeah. So here are the solutions. And now it is something very interesting, and I've already done it all my life, and I was happy to see that Donald Knuth writes this. He says that if you are at the end of the proof, then you can write by lemma 1, we conclude that blah, blah. It's kind of like decompression moment for the reader. If you're in a very intense short proof, just give him a break in the last sentence of the proof. So it's exception. I always write so it's clear. A person who perfectly understands the proof, he reads the last sentence, and I additionally say this finish the proofs, and then I put this square there, this QED symbol. So then the reader knows 3 times the proof is finished, but I do it to let him relax. Okay, yeah, but I lost the page number of the reference. So I hope I didn't dream that he wrote this. Okay. So yeah. So at the last slide, there are the references. So so Knuth is in the middle. He has a transcript of lecture notes plus a full YouTube series. Okay, so let's go back to dropping things. Yes. Better than removing unnecessary words, remove unnecessary sentences. So at the end of the introduction, there is this annoying sentence. The remainder of the paper is structured as follows, blah, 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 blah. And so usually it's very rare that you should write this. Just after your theorem, tell how it's proved. And then the reader will see from the subsection titles where are these, where he can find the different parts of the proof. It's like 90% of the cases it works. Is beyond the scope of the paper. So you can hear it if a person gives a talk and he has nothing to say, he will say at least 3 times, this is beyond the scope of the talk. It's just a person who really wants to say something in a short time will not use 10 seconds to say that something is beyond the scope of the talk. He will want to say something more interesting. So then we now prove the following theorem. So before you prove a theorem, you need some connecting sentence. But then it's nice if this connecting sentence contains some information. So before the end of the previous proof, you need a connecting sentence and then try to say something interesting. And then what is very ugly, unfortunately, I've never seen it for a long time, is called dangling theorem. So people say that theorem ends with a point. So why not use this point both as start of theorem and the end of previous sentence? But it's very disorienting if you read it. Okay, and the last thing I've already discussed. Okay, unnecessary punctuations. So almost never use exclamation marks, at most 1 in a paper, but better 0. Semicolons are out old-fashioned. In formulas, remove the unnecessary brackets. And important, don't use commas which aren't necessary. So here is if you are in doubt, then you should read it loud. And if you do not pause, there should be no comma. But okay, there are complicated rules because this rule is not enough to know whether there is a comma or it's enough to know whether, I think it's enough, but maybe the linguist can tell. So if there is no pause, there should be no comma, but no, one of the direction works. Yeah, but if there is a pause, it doesn't mean that you should place a comma, I think. So there you need some more complex rules. I think it's something like, okay, let's go to the next point. So you can make some simplifications again. So now we do a bit more than just dropping words. So let epsilon be an arbitrary but fixed positive number. Can just say fix epsilon to be positive, or let epsilon bigger than 0. Again, the same thing, there exists d such that for all c bigger than d, and then you have some expression that does not use d anymore. So d appears only once, then you can just say for large c. But again, the same discussion as before. Let us first observe that can be replaced by one word, note, is equal to 0. You can say shorter, equals 0. But I'm not sure if this always works. This leads to the contradiction with the maximality of f. This contradicts the maximality of f. So there are a few more examples. Okay, then there are more rules. So utilize straightforward vocabulary. So how can you say this better? So you can say it with easier words. You can say use simple words. So many people say utilize instead of use. Remove negations of negative words. So this is something that's never disliked. So how can you say it better? Use positive words, always appreciated. Avoid nounification. The official word is nominalizations. So that if you have a verb, you turn it in. So you have some activity, you describe it, you turn it into a noun. So again, this example, like the goal of the operation is the denazification of blah, blah, blah. So it's better to point to the activity because the activity can be understood. Okay. So yes, here are some sentences with with nounification. So in the first sentences, can you point out some nouns that hide activities? Two more, well, maybe even three, 2 or 3 more. And the first point.
If necessary.
Yeah, there is a necessity. Then, well, it's more an adjective that becomes a noun. And then there is more.
Appear.
Yeah, appearance. So when they appear. And then one can discuss a bit the last word, meaning. So say what they mean. So they mean something is again an activity. So the second text, okay, and how can you say it better? It's kind of like pushing down the reader a little bit. It's just, let's do one more and then continue. The derivation of one was done using an analog computation as in section 2. So how can you say it without nounification? So how many nounifications of nominalizations I should say? So you can say one was derived using in a similar, one was computed in a similar way as in section 2. Okay, here are some more rules. So don't use contractions, don't use abbreviations. So don't use abbreviations that you didn't declare before. So some authors write if with 2 Fs to mean if and only if, so don't write it. But you can use Latin abbreviations, but nowadays in recent papers I don't see them, almost never, but it's allowed. Okay, and so in the bottom, in the bad example is square integer between brackets SI. That's how people introduce abbreviations. But usually in math, there are other solutions. So you can use symbols, like in the last example. So just, I don't see any reason to use abbreviations in math papers. So then there is parallelism. So you should say the same things in a similar way so that the reader understands the analogy. So for example, parallelism can conflict with negation. So sometimes, so you want to do things parallel, but then suddenly the negation appears somewhere and then you use many negations. Okay, then there are sticky words like also and as well. And if you use them many times, it's a very unpleasant feeling. And so also avoid fast repetitions of also and as well as rare polysyllabic utterances. So utterances is extremely sticky word. If I will use it a second time in this seminar, you will immediately think about this sentence. And sometimes you want this. So if you have a few definitions and you want the reader to have strong associations, then you should do the opposite and find a sticky word. So again, it reminds me, like Donald Trump, he said crooked Hillary, but crooked is also a very sticky word. So now whenever, so he was in a competition with Hillary Clinton, so the opponent, and he consistently called her crooked Hillary. But afterwards, when I hear the word Hillary, I also think crooked. Although I think she was much less, I mean, he was worse than her, but he could make things appear different. Words are better than formulas. It's a statement of Paul Halmes. Paul Halmes has written an article about writing long time ago that's cited in any text about mathematical writing. And he insists on this. So, but there are also many people who disagree with this. And I think that has to do with the way how you internally represent mathematics. So here comes a deep thought. I think that there are visual thinkers and people who think with words. And older people tend to think more with words, while visual thinkers, they like formulas more. And I think there the conflict arises. Okay, but anyway, all people who wrote books that are read by thousands of people, they agree that words are better than formulas. So I'm teaching statistical learning theory in the computer science department, and there is a topic where I have only terrible textbooks, and the best one, half of the pages look like this. So half of the space is filled with sequences of formulas. So this is very stupid. Why? So that there is a sequence of formulas. Each formula, somewhere something changes. And the reader has to do full parsing of all symbols. Each time rethink what they mean, where they appear, go back into the memory, look in the algorithm, where is the line where something happens. And so to help my students, I have rewritten it like this. And so, so the bunch of equations, they are still here, but I've changed the context so that all cumbersome notation drops. So I've considered like 2 important steps. And so I told them, like, look what happens if this happens in the algorithm. And then I can write a few inequalities. Look what happens when this happens. Again, I write a few inequalities. And then in the end, I apply Cauchy-Schwarz to combine things. Well, in the original proof, Cauchy-Schwarz happens in the first step, and then both parts happen through each other, and it's very confusing. So what I wanted to say is, if you have a long chain of formulas or you have calculations, then you should think like, okay, how can I let the reader focus on some important ideas? So then you should think, what are the important ideas, and let the reader focus on it. It's very hard to give exercises on this. Just keep in mind, if you have computations, then probably something is not optimal. There are cases where you cannot avoid computations, but they are rare. And Paul Halmes says that you should write in advance. Unfortunately, I do not know a nice proof, and the best I can do is the following list of computations. Is the following computation. And also in your paper, you don't need to write the computation in detail. Usually the reader can do it by himself. Just make sure he knows all the tools that you're using. Okay. Then what formulas and punctuations. So a formula or a symbol or expression should be treated as a word. That means if a formula is at the end of a sentence, you write a point after the formula. If the sentence continue, if it was a word and you want to write a comma to continue the next part of the sentence, then write a comma. The second rule is that you cannot start a sentence with an expression or a symbol. And so the generic solution is just to repeat the type of the symbol. So the value blah blah is irrational, or the number is irrational, or but you can have sentences that consist only out of a mathematical expression, like in the last line. This is okay, and then you have to put a point after it. So it doesn't matter if the formula or expression is like inside the text or in a separate display. Okay. Then very common issue. It's called the overworked comma, but it's not a very bad issue. It's just the comma is used to separate two mathematical expressions, but then it becomes very often it becomes confusing, like in the second example. Hence, for all a bigger than 0, f a is bigger than 0. So there I should write it in more words. So when the reader sees two mathematical objects separated by comma, he thinks about a pair of objects. And that makes things confusing. Then there is another advice. So the symbol is an element from, should either denote the word in or is in. So for example, for every n in S, the value f of x is in S when you read it. So the first time it is in S, the second time is in S. This is bad practice. So it slows down the reader. So the reader will unconsciously pick up what's your use of the symbol element of. And then when you change to another use, he will use, his unconsciousness will be disturbed and he will feel uncomfortable. Same for equality, bigger than, and so on. Okay. And then there are I think this is obvious advice. I don't need to discuss it. So you're not going to use the letter n for something that gets for some small positive real. That's terrible. If you take the limit of n going to 0 over the real numbers, it's just terrible. Then people are very if you somewhere in your paper use complex numbers, then they say you cannot use a summation index. But in my opinion, it's not a problem. If you have a clear paper with not too many symbols, then you can use the few symbols you're using in different meanings. Well, if the context makes everything clear. So the first example is, of course, problematic. If you use the same symbol in two different meanings in a formula, that's terrible. Okay, this is kind of obvious things. Then I spend a lot of time thinking about which letter. So if I have a large proof, I need several letters. Then I want to help the memory of the reader. So if I have a set of bad points, I will call them B. And then a bit later, I have a set of big elements. I want also to call them B, but then I will just change the name and speak about large elements. Probably the linguist has to say something about this. I forgot what was the difference between big and large. It has a different, the words big and large, there is some subtle difference in meaning. Somebody told me once, but I forgot.
There is, but actually you have to go to, for example, Ausdijk dictionary and to see with which words it is combined. It is considered that large is a little bit more formal than big, because all short words like big are more informal. But I wouldn't bother about this. This is a very minor point.
Okay, yeah. Okay, so they are synonyms. Cool. Then if you use both integers small n and big n simultaneously, you better use small n for the smaller value. Okay, but then it's I don't like to use big N and small n at the same time, because it's annoying if you give a talk, because each time when you use n, you have to say big N or small n. It's very annoying. So you would use other letters. Okay. And then a very important technique to get a better paper is get rid of variable names. If you get rid of them, then you don't have to exhaust the memory of the reader. So there is a lemma: if E divides D and D divides Q, then E divides Q. So you can just drop one divisor. If D divides Q, then every divisor of D is a divisor of Q. I don't know how I can do further than this, because if you say every divisor of a divisor is also a divisor, it's not clear what the last part means. And then very often I show some expression and don't give it a name. And then I say the value of the above equation is blah, 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 of the product is blah, blah, blah. And each time I say product, it's very easy to memorize for the reader. If you say the product P, then each time when the reader sees P, he has to think what was P again. Okay, so this, that, and so on, they are very handy tools from language, but you need to make sure that when you write this, there is just only one point where it can point to. And also the reader will not understand as well as the sentence. So when the first time, when the reader reads the proof for the first time, he will have shaky understanding. So if linguistically this point can point to two places, but you rely on the understanding to eliminate one place, it's a bad situation, because you cannot rely on the reader understanding the proof upon forced reading, unless you're very confident. Yeah, so if you're very confident people, they can play a bit with this, very experienced people, but I'm careful about it. Okay. Then there is obvious advice: similar quantities, give them similar names. So if you apply a lemma only once, then you can so you can match the variable names from the place where you apply, and that's much less thinking. It's much easier. Like this, you don't. Okay. So here is some exercise. So let's go over it line by line, and then you can tell me what can be improved. So the theorem: there exist infinitely many prime numbers P. So what can we improve on the statement? So we can drop two things. The question is too easy or too hard? We can actually say, okay, one can discuss about this. There exist infinitely many primes. It's debatable of whether this is better or not. I am not sure, but okay. At least P we should definitely drop. So then the proof relies on the existence of prime decompositions. For me, that's okay. Then the lemma: every integer Q bigger than 1 is divisible by a prime. Thus I would change. I would drop Q, but then we have to, the larger 1 symbol needs to be written in text. So the lemma becomes longer, but it has fewer symbols. I would choose the second option. I put it in this. So I think the second is better than the first, but okay, it's debate. debatable. Okay, so then let's go to the proof. For the sake of contradiction, assume there exist finitely many prime numbers. Let P1 till Pt be these primes, and let Q equal to P1 Pt plus 1. Note that Q is not divisible by Pi for I smaller than T. So do you have remarks about this? Well, it's a bit too early maybe to discuss whether we can drop Q, but do you have other remarks? Okay, then let's read further. Since Q is bigger than 1, the lemma implies that there exists a prime R that divides Q. Can we improve this? Yeah, hence, therefore, this implies what there are more of them. I forgot. Hence, therefore, thus, we conclude. So there are like 5 things for the same, and you need to rotate over them. And here I've rewritten it without the Q. So I think it's better because now the only symbols that are used are P1 till Pt. Not many mathematicians do it, but I think everyone should do it because remarks is magic. Because at each remark, you look to what you said before the word remarks. I use it all the time, zero complaints. But maybe it depends on the field. But you can say it in a small sentence. We make 2 remarks and then just put the sentence after each other. Yeah.
I have a question, Bruno.
Yes.
Is it typical of mathematical papers to use bulleted lists like you did here? Whether it is notes or notes that, and then a bulleted list comes, is it typical? You have dash and dash. It looks like a bulleted list.
Inside proofs, it's not so typical. Like, well, I don't think that anyone I've never received objections against it, but I work in theoretical computer science, which is not completely the same as math, but I think it's fine.
Okay, thank you.
And then next rule where everyone agrees is that you should not use logical notation. But if you write down sets, I think it's sometimes unavoidable. But all references like Halmers, Knut, and all of them, they say never use exists in plain text. So don't use exist for all and the logical symbols, of course, except for papers and logic. Okay, then the last thing that I want to say, let's speak about proof structure. So beginner writers, they sometimes confuse proof by contradiction and proof by contraposition. So if you want to prove a theorem that's an implication, then you can negate both sides of the implication and flip the directions. So that's proof by contrapositive. And proofs by contrapositive, it's very pleasant proof, especially if you need to do research that involves this proof. You can modify, see clearly what happens, tweak some parameters. It's very pleasant style. Proof by contradiction means that you look at the negation of the statement that you want to prove, and then you prove that 1 equals 2 or something other that is a contradiction. And then you assume that this statement, that the original contradictory assumption is false. So that's how we prove that there exist infinitely many primes. But unfortunately, so usually the first time a person invents a proof, he uses proof by contradiction. So he says, I want to prove blah, blah, blah. Let's assume the opposite. And then he brute force, he applies anything he knows until something corrects. Something corrects means a contradiction is found. But usually these proofs by contradictions are false proof by contradictions. That means the contradiction appears only once in the end. And that means that you can turn around the proof and have a direct proof, which is usually much more pleasant to read. And so as a reviewer, this is in many papers, I point out that there is a false proof by contraposition, and you can say it more nicely, usually shorter, in the positive way. And so the proof of there exist infinitely many prime numbers, the one by contradiction is the one I've seen in all high school textbooks. It was in my high school textbook, and I think it's false proof by contradiction. Actually, I also think that the classical proof that square root 2 is not rational is also a false proof by contradiction. I would prove it by induction. But okay, let us go to the story about prime numbers. So what you're doing, you're getting finitely many prime numbers, and then you come up with a new prime number. And so by applying this procedure iteratively, you end up with an infinite list of prime numbers. And just that's a direct proof that there are infinitely many. And so when you look at in this natural way to the proof, you actually get an algorithm to compute infinitely many prime numbers. So yes, so the proof can be improved further. And then without loss of generality, we may assume that's a very heavy thing to say. And usually it's a sign that so you want to prove a theorem, and then you make an extra assumption that helps you in the proof. And then in the beginning, you say that this extra assumption can always be realized for some reason. Usually it's better to say this reason directly. For example, you have two parameters called A and B, and the statement is symmetric for A and B. So then people start by saying, without loss of generality, A is at least B. But that's a heavy sentence, so you can just start by saying we assume A is at least B, the case where A is at most, B is proven similarly. And it happened a lot that, well, it happens once, I was very surprised. So I had a proof where I used this and I thought it was essentially true. And then there was some old, very experienced mathematician, and he says, don't try this. And I say, I cannot find the more general version of the statements to do it directly. So it was about Turing machines, and I say, without loss of generality, assume that the machine starts by writing this on the tape. And then he said, let me think. I went to the toilet, I returned, and then he said, here is your generalization of the proof. And a lot of things fell out of my proof after I realized this generalization. So the gain by removing this was a lot. The statement of the theorem does not change if we replace each appearance of A by B and vice versa. So then we can, so I didn't write it in the slide, but I say, imagine we have a theorem that has this property, then we can start our proof in this case. And then subscripts. So the people use subscripts to point out unimportant technical information. And so if you use subscripts, you should try to get rid of them. So in our proof before, we say we use the list of primes. So we can suppress subscript by just giving the set of primes a name, for example, capital P. But then, of course, disprove infinitely many primes is for high school students, so that they don't know symbolic summation. So for them, it's not a good solution, but in general, we can do it. So yes, so I would say if you want to make your paper ugly, use many subscripts. And then if you have double subscripts, I think in my experiences, in most cases, you can remove at least one of them by fixing something somewhere in the proof, or by even restructuring a little bit the notation. And so the worst is double subscripts. Like in computer science, there is a definition of subsequence, like all books, not all books, but many books, they do it with double subscript. You can see it, yj is equal to xi subscript j. And so this is very cumbersome to parse, very ugly to write. And if you think a little bit, you should think about higher concept. So if you have concatenation of strings available, then the second definition is better. And then there is like a very spectacular example. So another reference about mathematical writing that's cited a lot is by Gilman from 1987. And in his appendix, he reduces a very famous paper to half its size just by being wise and fixing the subscripts. So all lemmas become unnecessary. So he changes the notation of certain sequences, and then the lemmas becomes something equals the same thing. And the whole proof disappears. For beginner mathematicians, I want to point out some resources. So there is Grammarly and Pro Writing 8. They're just amazing online tools that tell you all your grammar mistakes and spelling. And so I agree with them like 98% of the cases. I would say that, well, last time it was disappointing. Like 1 in 10 times I disagreed. So what you have to do, you have to copy paste your text after you compiled it with LaTeX, and then copy paste it on their website. For Grammarly, it's in Ukraine, so you need VPN. And Pro Writing 8 students told me it's very good, but I haven't checked myself. Yeah, there is English advice for Russian mathematicians. There is a book, Sosinsky. It's in the last slide. There is a full reference. It looks pretty impressive, precisely what you need. And then LaTeX. So overleaf. Now all my co-authors want me to use overleaf. I hate it, but I tell you that it's very popular. Then if but that's for young students who don't know what is LaTeX. I can tell you all mathematicians use it and they love it. And it's very efficient in the long run. So if you work for several years, there is no discussion. And then if you have questions, you put it in Google, and Google brings you, finds your questions on the website Tikz Stack Exchange. And then finally, there are the references that I use to prepare the stock. And then I will hope to see all your talks in the best mathematical journals in a few years.